Welcome to 4.3, where we're going to look at more trigonometric functions of angles. On the previous lesson, we looked at how the unit circle is related to the sine functions. But I did allude to the fact that there's actually a bigger picture here with that. So what we found is that if we look at the angle theta here, that opens up to a point here on the unit circle, and the unit circle, of course, is 1. So the distance from here to here is going to be 1 because it's, at the center going out to the unit circle. That the values of x and y, the coordinates for that point, are certain values. And in fact, we say that cosine, definition-wise, cosine of that theta is equal to the x value on that unit circle, and sine of theta is defined as being the y value on of that point on the unit circle. Now, if we continue that ray outward, and you can see here we're doing that, and we stop at any point, and so we just say xy, because it could be any point along this line. It also creates a triangle if we draw from that point to the x-axis, a right triangle, in fact. And what we see is that the values that we have there, let me just kind of label through here so it's clear what we're talking about. So the distance from here to here is my x1, and the distance from here to here was the y1, right? It's the height and the horizontal distance of that triangle. And in the case of the unit circle, the cosine, remember, opposite over hypotenuse, which is the sine, opposite over hypotenuse, would be y1 over 1, because the hypotenuse in a unit circle is 1. And this also would be 1. So we're not giving up on that idea that it's also a ratio, right? It's the x value divided by the hypotenuse for each of these. And then the other ones are different iterations of that. Well, drawing the other triangle here, we end up with a similar triangle. These both all have the same angles, because both of these, if we draw it perpendicular to the x-axis, have a 90-degree angle, and they both share this angle. So that determines this angle and this angle. In other words, they have to be the same angle as well. So those are similar triangles. So we could say that OQ1, P1, which is my smaller triangle there. Q1 is this point here. P1 is my point on the unit circle, is similar. Let me try that again here. Is similar to OQP, which is the larger triangle there. If they have the same angle measurements in our triangle, then the two triangles have proportional sides. So if I take the length of x, which is the distance from here to here, this is x, and the distance from here to here being y, oops, not y1, just y, because we see the point here, xy. So we're just representing those. This would be, cosine theta would be x over whatever the r is, r being the distance from here to another point along here, xy. And the y would be y over r. And these would be equal to the x, which is also equal to the cosine of theta and the sine of theta. This remains true for tangent as well, and all the other iterations which are reciprocals of these. Tangent would be opposite over adjacent, y over x, which is equal also to y1 over x1. So let me just put that first, and then we'll put y over x. So we've got all of these different things that we can set equal to each other, and they're proportional. As long as we're representing the same sides, then they are equal to each other in their proportions, their ratios. So for any points outside then of the unit circle, we can still look at their side lengths of the triangle that's formed there, where r is more than 0, obviously, because r is a distance. It's equal to the square root of x squared plus y squared. And we get all of these ratios, the ones that we talked about on the previous page, but then all their iterations as well. Notice that we have x can equal 0, y can equal 0. Whenever we have a denominator value, we have to kind of clarify that, kind of a technicality there. So let's look at another angle. Let's say we have an angle, and actually we don't even know what the angle is. We'll just say it's theta, but it is something, as we can tell by the picture, that contains the point -1, 3. Since we have -1, 3, we know that puts itself into the second quadrant here, because the only way we get a negative x is if we've moved in this direction. So at any rate, -1, 3 is my point. Can we find the exact values of the 6 trigonometric functions of theta? And the answer is, of course, we can. Now, I do want to mention something which is going to come up here in a little bit, so I figured this is actually a good visual opportunity to reference this. But notice how, because of the location of the point, if I were to try to draw a line that creates a 90-degree angle with the x-axis, right, that it would have to come right here. I wouldn't be able to go this direction because it's not going to make a 90-degree angle. The only way I can make a 90-degree angle is something that passes through that point and lands over here. So let me just draw that in here. So that gives us a triangle that's not containing the theta that we're talking about here, right? So we do have something we call a reference angle or a reflexive angle. And we're going to talk about this here in a little bit, but the reference angle or reflexive angle always goes back to the x-axis, and we can look at it from this perspective here. We call it theta prime. And because they share a terminal side there, the values that we get for our trigonometric functions will be exactly the same. This was -1, this is 3. Okay, so we can think of it as, well, we can think of it as sine of theta. Sine of theta is opposite over adjacent, or opposite over hypotenuse, sorry, and we don't have the hypotenuse yet. And remember, we don't know that it's 1. It probably is not, because my values are outside of the circle with the 3 there. So, what do? Well, we just have to find that. Remember that before I do this, let me just get this out of the way. Before we do this, we need to know the values of all sides. We know that radius is equal to the square root of x squared, so -1 squared, plus y squared, which is 3 squared. So that gives me the square root of 1 plus 9, which is the square root of 10. Can 10 be simplified? Well, we have to look for perfect squares that might go into it. The smallest perfect square, well, of course, is a 1, but that doesn't reduce that at all. The other one would be 4. 2 squared is 4. 4 doesn't go into 10, and then we go to 3, and that's 9. 9 obviously doesn't go into 10 either. So r is simply equal to the square root of 10. I'll put that there for reference. But at least we have the visual of this triangle here. And because they share the same terminal side, all the sine, cosine, all the trigonometric functions are the same. So sine of theta will be equal to the opposite over adjacent. Remember, this is so, ka, toa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, tangent is opposite over adjacent. For sine, it's opposite over hypotenuse. That would be 3 over the square root of 10. We don't like to have square roots in the denominator, so I'd multiply the top and the bottom by the square root of 10. That gives me 3 root 10 over 10. And if 3 could simplify with 10, we would do that, but in this case it doesn't. Cosine of theta would be -1 adjacent over hypotenuse, so -1 over square root of 10, which, when we rationalize this denominator again, we get negative square root of 10, or -1 square root of 10 over 10. Again, can't cancel anything there. The 10's underneath the square root, so it's kind of safe. It doesn't have a value of 10 anymore. It takes on a different value. Tangent is opposite over adjacent, so 3 over -1, so 3. Then we go to cosecant goes with sine. This is going to be cosecant, the reciprocal, so root of 10 over 3. The secant, which is the reciprocal of cosine, is root of 10 over -1, or negative root 10 over 1, which is just the square root of 10. And then tangent, cotangent of theta is equal to the reciprocal we have there, so -1/3. Also notice here that we had a few that ended up being negative. The ones that were negative in the second quadrant there were cosine. I didn't mean to do that. Not trying to cross it out. Now it erased it. Let me just put it back in there. Cosine theta. And then its other reiteration there, it's reciprocal. Secant theta. And then tangent and cotangent. Just highlighting these in green. I guess I could have just underlined them. But these are the ones that in the second quadrant we see are really always going to be positive. Why? Because they both involve an x. This is supposed to be negative here. Right? Sine is opposite, or the y value, over hypotenuse, and y is positive in this quadrant. And x is negative. So sine and cosecant are the only ones that involve non-x's within their calculations, and so they are the only ones that are positive. So looking at, the trigonometric functions in general, in the first quadrant, they're all going to be positive. In the second quadrant, we have sine and its reciprocal, and all the others will be negative. So sine is the only two that are positive, and the others, cosine, secant, tangent, cotangent, all negative. In the third quadrant, remember, tangent is made up of y over x, and both x and y are negative in the third quadrant. And so a negative divided by a negative, whether it's y over x or x over y, is going to make it positive. Negative. So tangent and cotangent both involve only x and y's. The others involve an x and a y, which will both be negative, but then they're both over hypotenuse, or the hypotenuse over the x or y. And then the last one, cosine, x is positive, so cosine is the x, secant is its inverse, and everything else is negative because it's below the x-axis, and those involve y's. Okay, let's put an official definition to what I was talking about earlier with the reference or reflexive angle. So if we let theta be any angle in a standard position that is not a quadrantal angle, meaning it's not touching the axes, right? So the angle it's not 90 degrees, 180, 270, or 360. or 0 or anything like that. So it's not a quadrantal angle. The reference angle theta is the positive acute angle theta prime, formed by the terminal side of theta and the positive or negative x-axis. So like I said earlier, it kind of always goes back to the x-axis. What the relationship here is that they will share the same trigonometric functions. So whether I look at it from one perspective or the other, they share the same angles. Let's just look at what we have here. So for example, if it's an angle that's in the first quadrant, theta we say is equal to theta prime. They're the same. There is no other reference angle. It's the same thing. But after we go bigger than 90, that's when we start, in order to look at it from a triangular perspective, we would need a theta prime. And theta prime would be whatever we get from 180, which is all the way over, and then subtract out this amount. So subtract out this, what we have left is that angle there. That's our theta prime. From a radian perspective, that would be pi minus theta. Pi, remember, is akin to 180 degrees. If we're in the third quadrant, then we need to subtract our angle theta. We have to go theta minus 180. So we take away 180. And if we, so basically we're taking this angle here, and then we're saying let's subtract this amount, which is the 180 part. What we're left with is that guy right there. And that would be theta minus pi as well. For quadrant 4, we're going to take this angle that we have, and we're going to go 360 minus that angle. That gives me, so if we take the whole amount and then subtract out this, what we have left is that. So in finding the reference angles, I always find it helpful to first figure out what quadrant they're in. And that's fairly easy to do. You might have a little more trouble if it's in radians, because we're just not used to that yet. But let's go ahead and see if we can figure this out. So first one is theta equal to 250. So we know that from here to here is 250. And if I keep going, we're at 270. So it's going to be somewhere right before 270. And to get this, we're going to take our angle. So theta prime is going to be my angle, so 250, but then take out the 180. Excuse me. So that gives me 250 minus 180 is 70 degrees. So I know that from here to here, this is 70 degrees. The red. The green, of course, was 250. So 70 and 70, that's in the third quadrant. We have to know what quadrant it's in. And 250 will have similar trigonometric outcomes. For B, we have, I'll draw another one, 3 pi over 5. This is not one of our common ones, but again, it kind of helps us to think about pi, it helps us to think about what pi over 5 is. Pi over 5, if we just look at that, pi divided by 5 is 180 divided by 5. And 180 divided by 5, I'm going to write this over here, 180 divided up 5 ways is 36. And so with pi over 5, if I have 3 of those, that's 3 times 36. We know 3 times 30 is 90, so this puts us a little bit more past 90. 6 times 3 is 18, so at 108 degrees. But again, we're not trying to translate these here. Oh, I'm sorry, 118, not 100. No, that's right. 108 degrees. I'm just doing this in my head. All right, so what does that mean in terms of so we're in the second quadrant. That's the main point I wanted to establish there. And so we know what's positive and negative and everything like that in the second quadrant. But what would be the reference angle? Theta prime. Theta prime, so when we're in the second quadrant, is pi minus our angle, which is 3 pi over 5. So I translated it for myself into into degrees. But there's other ways to do that, but that's just one way you can do it. Figure out what it is, 3 pi over 5. But now we're going to take 180, or pi, and we're going to subtract 3 pi over 5. To get it so that they have the same denominator, we can go 5 pi over 5. And 5 pi over 5 obviously is equal to pi because the 5's would cancel. And 5 minus 3 pi is 2 pi over 5. So my reference angle would be 2 pi over 5 in the second quadrant. C, theta equals to 5.75. This is kind of a weird one. We're not quite used to that. But what would that be in terms of quadrants? Well, first of all, is it a degree or is it a radian? Here we need to look at what symbols are being used, and really there's no two symbols, or there's no symbol for that, so we assume it's a radian. Radians are just real numbers. Sometimes we write them with pi's and all that, but when it comes down to it, it's just a real number. So, being as unfamiliar with these as we are, and if we're thinking in terms of degrees, this would seem like, oh, it must be in the first quadrant. But keep in mind that 5 actually in radians is not a small value like it would be with degrees. So one thing we can remember is like, what is 2 times pi? Because remember, 2 times pi is 360, one trip around the thing. So what is 2 times 3.14 approximately? 2 times pi is about 6.28. And so if I go all the way around, I'm at 360, 2 pi, or 6.28. So 3.75 is looking like it might be in the fourth quadrant. Let's make sure, though, that that's where it is. Maybe it's in the third quadrant. Well, let's take into account what this is. This is 3 pi over 2's. Pi over 2 is 90, so this is 1, 2, 3 of those. So if we go 3 times 3.14 divided by 2, we see this is approximately 4.71. So 5.75 is somewhere in the fourth quadrant because it's less than one complete rotation, but more than only 3/4 of a rotation. So it's going to be somewhere in here. In the fourth quadrant. And so that's going to determine, if this is theta, what theta prime is. Theta prime, one of your reference angle always needs to be positive, so keep that in mind. We're referencing it from the x-axis to the terminal side in the other direction, and so it's always going to be angle that's positive, right? We always want to think of it in terms of a positive angle. So theta prime, and it has to be between 0 and 1. 0 degrees and 90 degrees, or 0 degrees and pi over 2 degrees. So theta prime is going to be 2 pi minus whatever we have there. In this case, our theta is 5.75. So 2 pi minus 5.75. So we're just going to approximate this. So 6.28 minus 5.75. The theta prime is approximately 0.53. We also will have, many times have angles that have gone through more than one rotation. And in fact, there's an infinite number of rotations that a angle can go through. If we're talking about sine and cosine, which are kind of the basis of all this, sine theta would be equal to sine theta plus 360 as many times as possible, right? N being an integer, so a whole number. It just represents really the number of times we've rotated, and this could go in a positive or negative direction. And in radians, 2 pi n. 2 pi n just, again, would be a whole nother rotation in addition to the theta that we've already taken. So let's just find a summary then of how we approach finding the angle that's given to us in a trigonometric function that they want us to evaluate. One of the things that can happen is we can have thetas that are more than one rotation. So if our theta is greater than 360 or greater than 2 pi, then we want to find the coterminal angle for theta between 0 and 360. So in other words, we want to figure out, we can keep on subtracting 360 until we get something that's between 0 and 360, or if it's something greater than 2 pi, keep subtracting 2 pi until we get something that's less than 360, less than 2 pi. So in other words, figure out what is it within one rotation. If it's not, then we go straight to step 2. We just want to find the angle theta prime, so find the reference angle that results from step 1, and then write the trigonometric function of that. And 3, choose the correct sign for the trigonometric function based on the quadrant in which theta lies. Keeping in mind that where each of those is negative, where each of those is positive. So let's work through a couple of examples here. We have find the sine of 1320 degrees. Well, 1320 degrees is obviously more than 360. Okay, we can start with that. Something in the thousands is more than 360. So let's just start subtracting 360 from that. So we have 1320, subtract 360. That gives me 960, still too large. Let's subtract 360 again. That gives me 600, still too large, minus 360 again. That gives me 240. There we can stop. So now I know what the angle is. 1320 is 240. We know that it's in the third quadrant because it's more than 180 and less than 270. And thinking back to the reference angle, what this would be, if this is 240, let me draw it back here. The reference angle here, theta prime, would be 240 minus 180, which is 60 degrees. 240 minus 180, 60 degrees. -8, 60. All right. So now if I want to find the sine of that, I just want to think about what the sine of 60 degrees would be. The sine of 60 degrees is Well, we can go back and reference our chart for all of those common. This is one of those common ones that we see. But the sine of 60 degrees is the y value, and that is square root of 3 over 2. So sine of theta prime is the sine of 60, which is square root of 3 over 2, and y in the third quadrant is negative. So for the sine of 1320, we have the square root of 3 over 2 negative. That would be the y value. So here's how we could kind of write this out in progression. The sine of 1320 degrees is equal to the sine of 240 degrees, right? Those are exactly equal to each other. In fact, it reaches the exact same terminal point. But it's not the reference angle. The reference angle was 60. So I'm going to go the sine of 60. And I know that puts us in the third quadrant, so it's going to be negative, whatever it is. The sine of 60 is square root of 3 over 2. And so we have the negative root of 3 over 2. So let's do this a couple other times, and if you want to pause the video at this point, you can try the tangent. These are common outcomes, just because that's the kind of angles they're going to give us here, that we don't want to do using our calculators. So we're not using our calculators. We're using those charts that were given on the previous and that are also in your book. Those are a great thing to print out and have handy, or to write on a note card or something to that effect. All right, so now I'm going to go through and we'll solve these. So we first started out with 840. So again, I'm going to do the same strategy. I'm going to keep subtracting 360 to see what I get. And this comes out to be 480. So I can tell all you need to do is subtract it one more time. 0, 2, 1. This would be 120. So that puts us in the second quadrant. 120. And 180 minus 120 gives us 60 degrees. So 120, which is the same as 840. Okay, second quadrant, what is tangent? We know tangent is negative here. So I can say the tangent of 840 is equal to the same tangent of 120, which is going to be equal to the negative tangent of 60, which is the negative square root of 3. Since we know tangent is negative in that quadrant, whatever tangent comes out to be for, 60, basically, we just want to use that same number. A lot of these common things that appear, the only thing that changes is the sign, depending on what quadrant they're in. So it isn't necessary to even have to memorize the entire table, but just the key ones within the first quadrant. And then we can attach the signs based on the reference angle and the quadrant that they're in. Okay, so let's take a look at B there, which is the secant of 59 pi over 6. Obviously a very big number on top, not what we're used to seeing in terms of radians. We know that each rotation around is 2 pi, but remember with this 59, we need to remember it's being divided by 6. So let's put it into what one rotation would be with 6 as a denominator. With 6 as a denominator, I want our division by 6 to give me 2. So 2 times 6 is 12. 12 pi divided by 6 is 2 pi. So 12 pi over 6 is the same as one rotation here. Now there's a couple of ways to approach this. We can just keep multiplying 12 until we get the highest number that's still less than 59 if it doesn't go into it evenly, which it will not. The other way to do it is to look at 59 and think, what is the next largest number that 6 will go into, which is actually very close in this case, 60. 60 pi over 6 would be 10 pi, which would represent, since 2 pi is a full rotation, this would be 5 rotations. 5 complete rotations around the thing. So if I'm only going 59 pi over 6s, that means I haven't quite completed 4 rotations, which means I did 4 rotations. 4 times 12 would be 48 pi. 48 pi. That would be 4 rotations. Plus we went a little bit more, not quite 5 rotations. 59 minus 48 is 11 pi. So I did 4 rotations plus almost a full rotation, but I was 1 pi over 6 short of it. So really breaking this up, this is 48 pi over 6 plus 11 pi. Oops, I turned my 11 into a pi. 11 pi over 6. This is 6 goes into 48 4 times, so 4 pi. No, I'm sorry, 4 rotations. Let me clarify this. This would be 8 pi. 6 times 8 is 48, so 8 pi, which is 4 rotations, because remember, 2 pi is 1, so if we divide 8 pi by 2, then we get 4. So 4 rotations, plus almost a fifth one. Let's take a look at it from an angle perspective. 11 pi over 6 would be almost to 12 pi over 6. Remember, pi over 6 is 30 degrees. So we want to draw something that's about this 11 pi over 6. And we can really just ignore this part because that's just rotations that end up in the same places. So we want to find the secant of 11 pi over 6, which the reference angle here would be 2 pi or 12 pi minus 12 pi over 6, which is 1 full rotation, 12 pi over 6, and subtract out 11 pi over 6. That gives me just pi over 6. So that's all that's left here is 1 pi over 6. Secant is paired up with cosine, and cosine is an x. And so cosine is positive in the fourth quadrant. It's positive here, and it's positive here. So therefore, secant is the same thing. So let's write out all of this. So my secant of 11 pi over 6, or 59 pi over 6, is equivalent to the secant of 11 pi over 6. Secant connected to cosine is, cosine is ca, right, C-A-H, adjacent over hypotenuse, so x over hypotenuse. Secant would be the opposite, so hypotenuse over x. But regardless, when we look at secant or cosine at this, it's square root of 3 over 2, so secant would be 2 over square root of 3, which now we would need to rationalize the denominator here, multiply the top and bottom by root 3, 2 root 3 over 3, and positive because it's in the fourth quadrant. So just to quickly summarize what we did here, we narrow it down, we take away until we get it into something that's between 0 and 360 or 0 and 2 pi. So we did that here. We figured out that 11 pi over 6 was the value that's between 0 and 2 pi. We figure out what quadrant that is, what the sine is, and we figure out with my reference angle what that would be equal to. And in this case, the reference angle was the secant of pi over 6. Same thing, and it's positive. So I can just keep that positive here. So narrow it down to what is between 0 and 360 or 0 and 2 pi. Figure out what the reference angle is. Find the value of that reference angle for the given trigonometric function, and then attach the sine of that particular trigonometric function in that particular quadrant. Let's take a look at a application problem. This one's involving the flight of a golf ball. The golf ball is hit on a level fairway with an initial velocity of 128 feet per second and an initial angle of flight of 30 degrees. Find its range, which would be the horizontal distance it traveled, and find the maximum height. Use the height equation. They give us the height equation here. To determine the height and the distance equation, they give this to us. So these are all given to us to determine the horizontal distance of the ball. All right, so we're going to start with the height equation and plug in the values that we know, so we'll adapt it to this particular situation. So my height is going to be the initial velocity, v sub o, which is 128, times seconds in t, and then sine of 1/2. We're going to subtract 16 t squared. Simplifying this out, I know the sine of, not the sine of 1/2, the sine of 30 degrees. Probably like, where did that come from? Well, it's because I knew what the sine of 30 was going to be. Sine of 30 is 1/2. So 1/2 times t times 128. And we can go ahead and combine those together. 128 times 1/2 gives me 64t. We have that minus 16t squared. That's my height equation. We could also factor this out. We can tell that this is a quadratic equation, but both of these contain a t, and they both contain a 16. And while I'm at it, I'm just going to go ahead and factor out the negative part as well. It's just going to help me see things a little clearer. So if I factor out the negative 16, which is the common factor between 64 and 16, and positive and a t, I'm left with, for the first half there, negative 4, and for the second half, positive 4, 16 divided by 1. Nope, that's not 4 anymore. That's just t. In other words, negative 16t multiplied by t minus 4. This would be that equation, just, written differently. But I can tell two things. Like, for example, this is my height equation. So if I had 0 in here, so I had a height of 0, I could see the t solutions are going to be 0, so time equal to 0, basically before we fit the ball, and 4 seconds. So 4 seconds will be the time before it hits the ground. So it'll reach its height, and then it'll fall to the ground after 4 seconds. That's going to be important for us when we get to the second half. But this is a negative t squared, so it is going to give us a upside-down parabola, right, because of that negative that's in front of the t squared. What we want to figure out is what is the vertex of this parabola. So how can we find that? Well, with a parabola that's in standard form. Here's what I call the standard form. Oops, I just erased it. ax squared plus bx plus c is my function when it's in what I would call standard form. And when we have it in standard form, we can take the opposite of b over 2a and then find that value, plug it back into the function, so find the f of the opposite of b over 2a. This will give me the ordered pair of my parabola. And the reason why we want to find this is the y represents my h, which is the height, and we want to find the maximum height. The maximum height is going to occur at the vertex. So for this particular equation, I have A is going to be negative 16, and B is 64. So taking the opposite of B, that would be the negative of 64 over 2 times A. A is negative 16, which is 32. So that gives me 2. Negative 64 divided by negative 32 is positive 2, which is my x value, and in fact tells me how many seconds it's going to take for me to get to this maximum height. And to figure out what the height is, I need to plug 2 into the function. So if we plug it in down here, we can see this would be negative 16 times 2, which is negative 32, times 2 minus 4 is negative 2. So that's positive 64. So we get, after 2 seconds, we're at our height of 64. So that's the ordered pair here. We reach our maximum height at 64 feet. Let's look at the distance then that it travels after 4 seconds. And this was given to us by another question, or another formula, where the distance is the v sub o, so my initial velocity of 128, times t, times the cosine of theta, which was 30 degrees. Looking up cosine 30 degrees, we knew sine was 1/2, so cosine takes on that other value at that point, root of 3 over 2. And so in simplifying this out, we can cancel out the 2. That leaves me with 64. So 64 square roots of 3 times t, or t is in seconds. This is distance for this particular ball. So really what we want to look at, and we're assuming here, of course, the ball doesn't bounce, which that would be an interesting situation. But I guess it said when it hit the ground. So how far it goes when it hits the ground, not after it rolls, after it hits the ground. So that, I guess it still works. But we know that's going to happen at 4 seconds. All right, we saw that when we looked at the solutions earlier. Let me go back to really quick. Right here, we saw that right here, sorry. When we factored it out, we set it equal to 0. We found that 4 and 0 and 4 were both the two solutions of this. So therefore, I know that I want to find the distance traveled at 4 seconds. So 4 is what I want to plug in for t. So we have 64 square roots of 3 multiplied by 4. This is approximately 443.4 feet. So that's how far horizontally our ball has traveled. Looking at a few more of these relationships that we have here with the trig functions, some of these are a little bit self-explaining. But if you remember, cosecant and sine have a reciprocal relationship. So this is just another way we can express that relationship in terms of a reciprocal. The cosecant of t, by definition, is 1 over, or the reciprocal of the sine of t. Secant and cosine have that same relationship. Tangent and cotangent. And then we can switch the places of all these. They are all reciprocals of each other. Tan, we can look at, remember tan was y over x, and cotangent was x over y. We can also look at it in terms of sine, because sine is y. So sine of t over cosine of t would be the y over x. The cotangent of t, cosine, and sine would be the x over y. And then we have these identities here, which kind of go back to the Pythagorean theorem, remembering that this is x and this is y. It's basically like x squared plus y squared equals c squared. Well, in the the c squared would be like our hypotenuse, right? And with cosine and sine and the unit circle, the hypotenuse is 1. So these are some relationships we can exploit to help use them to help us find unknowns when we're given certain things. So best to look at it from an example. We're given sine of t is 1/3 and cosine of t is negative. Find the cosine and tangent of t. All right, so it looks like sine is positive, cosine is negative, and sine is 1/3. So where sine is positive, cosine is negative, looking at our quadrants, we see sine is positive, sine is our y, so it's positive above the x-axis, and cosine is negative to the left of the x-axis. So we can tell that it's going to be here in quadrant 2. We'll just keep that in mind. Now we're going to use this to find cosine and then eventually tangent. So let's first set it up with our Pythagorean theorem. I'm given the sine, and I'm given clues about the cosine, but this is enough for me to find cosine, because sine squared plus cosine squared, I think we're using t there, so I'll take out the theta. Less confusion that way. So sine squared of t plus cosine squared t equals 1. So since sine of t is 1/3, that's 1/3 squared, cosine still unknown, equals 1. So this, of course, is 1/9. So 1/9 plus cosine squared t equals 1. Let's go ahead and subtract that to the other side. And 1 minus 1/9 is 9/9. 9 divided by 9 is 1. They have a common denominator, so we see it's 8/9. And that's the cosine squared of t. Notice the way we write it. We don't write sine or cosine of t squared, because that would confuse what we're squaring. We don't want to square the t, the angle. We want to square the result of taking the cosine of t. So we put the square next to the cosine and to the side. Let's solve this for t then. I'm going to take the square root of both sides. Cosine of t then is equal to the positive and negative square root of 8/9, where the square root of 9 is 3, so I can write this as the square root of 8/3, and 8 can simplify. 8 is 4 times 2, so I can break up that square root of 8 as the square root of 4 times the square root of 2. That becomes 2 root 2. So 2 square roots of 2/3 is the cosine of t. And that's half of what I'm after. Now we want to find the tangent of t. Now, this was, let me go back here. This was positive and negative. That's because there is a positive and negative 2 root 2/3. But we're told that cosine of t is negative, so we're only going to pay attention to the negative one for this problem because it's in the second quadrant. Okie doke. We don't really know what theta is, right? But we know what quadrant it is. So we know it's got to be somewhere between 90 and 180. Let's find the tangent of t then. Tangent, we know, is sine over cosine. So sine is 1/3, and then so we have 1/3 divided by the negative 2 root of 2/3. So that tells me that the tangent is going to be negative, but this is a very complex fraction. I'm going to change it into a multiplication, right, because this is a division. So we change it to a multiplication, then we flip the second fraction. So making that 3/2 negative 2 square roots of 2. If we do this multiplication now, we will have the result of tangent. And so the 3's can cancel. We see that. We like that. So that gives me 1 over negative 2 roots of 2. And we can get rid of this square root of 2. We don't want a square root of 2 on bottom. So if I multiply the top and the bottom by just the root of 2, because that's all I want to get rid of, that gives me the root of 2 over root 2 times root 2 is 2. So that's negative 2 times 2, so negative 4. So the negative square root of 2 over 4 would be the tangent of this t. So both tangent and cosine were negative. And we know that happens with tangent in the second and the fourth quadrants. So we know that that is correct. All right, so here we're given a clue as to the, we're given that secant of t is equal to negative 2. Secant of t is negative 2, and the tangent of t is positive. So thinking in terms of my quadrants again, if I have tangent is positive, that happens in the first and the third quadrants. And secant is negative. Secant has to do with cosine. Cosine is negative here and here. So that tells me it has to be in the third quadrant where my angle T is. All right, that's just going to help us if we have to find something that isn't listed, but here they just want us to find the tan of T. Tangent and secant have a relationship. In fact, here is the relationship. And so let's go back. So 1 plus tangent squared of t is equal to secant squared of t. So we're given a value for secant, and I want to find tangent. So I'm going to subtract 1 on both sides. That gives me the tangent squared of t is equal to secant squared of t minus 1. The secant of t was negative 2, so that's negative 2 squared minus 1. So that's 4 minus 1, which is 3. So tangent squared t is equal to 3. Taking the square root, tangent of t is equal to the positive and negative square root of 3. Whenever we take the square root of both sides in the process of solving an equation, we always take the positive and negative. But in this case, we're told that t is positive because we're in the third quadrant, so we can go ahead and just ignore the negative there for tangent. So the tangent of t is equal to, in the third quadrant, positive square root of 3. If you remember our discussion about even and odd trigonometric functions, we didn't discuss it with trigonometric functions, but even and odd functions, remember that we can tell whether something's even or odd by plugging in a negative x, and if we get the exact same function, f of x, we say that's an even function. And it's odd if when we plug in negative x, we get the negative f of x. So we get the very opposite of the original function. And this remains true also for trigonometric functions. And what we find is that with cosine and secant, they have a relationship, right? They're both related to x. So at any rate, if we take the cosine of negative x, we're going to get a positive x. And the secant of a negative x would be a positive secant. And so we say those are even functions. Of course, x there is a... let me draw the things here. X here is in the first quadrant, and the fourth quadrant, cosine is positive, right? All the x values are positive in this direction. So it's positive here and positive here. And if we take a negative equation, so let's just take it to here, the x, the cosine, is still positive, right? Just as it is up here. So any x is going to be the same in these two quadrants. The x value will not become negative. But if we go further, normally we would get a negative x here, right, in this quadrant, here, and that will remain the same with, if we're going in a positive direction. So the x's are still the same value. They would both be negative here, they would both be positive here. And so that's what makes cosine and secant, because it's related to cosine, even. With sine, let me start this over here. Why is this not working? Okay, let's look at sine then. For sine, when I'm in the first quadrant, so we're going positive x degrees, sine is positive. Sine, in fact, is positive since it's y in the first and second quadrants. And so would cosecant. So it's just a reciprocal of that. But if I go negative x, so I go in this direction, the same amount, notice that the y value will be negative. It'll be the opposite of what it was when it was positive. So the negative, or the sine of negative x going in the same number of degrees, but in the opposite direction, gives me a similar y to what I had, but the opposite sign. And that's going to continue to hold true. I'm going to get a negative sign over here as well, where normally I would get something positive over here, and so on and so forth. Let's put these into practice and kind of get an idea, get a grasp on what it is we're talking about here. So we're starting out with the sine of negative 30 degrees. We know that the sine of positive 30 degrees, sine of positive 30 degrees is 1/2. So sine being an odd function, we know that the sine of negative 30 degrees is going to be the opposite of that. It's going to be negative 1/2. Let's take a look as to why. Just visually, 30 degrees that may not be exactly 30, but at any rate, we know that the cosine is root of 3 over 2, and the sine is 1/2. If we go the same direction, but the same amount, but in the opposite direction, negative 30 degrees, you'll notice that the x value is still the same. Right? The x value of this is still root of 3 over 2. But the y value is the opposite of what it was before. Here it was 1/2. Here it's going to be the opposite of that, negative 1/2. Now, had this been the cosine of 30 degrees and the cosine of negative 30 degrees, these both would have had the same outcome, root 3 over 2. So that's where we see that when it's negative, we get the same when it's cosine, meaning this is an even function. When it's negative for sine, we're always going to get the opposite sign because it's sine. Okay, let's go to cotangent. This is an angle that is obviously more than one rotation. In fact, if we look at, what would be one rotation would be 8 pi over 4. 8 divided by 4 is 2, so that would be 2 pi, so that's one rotation. And so 2 rotations would be 16 pi. So at any rate, let's just take it as positive 19 pi over 4. If I take away 8 pi over 4, that gives me 11 pi over 4, which I can still take away another 8 pi, and that leaves me with 3 pi over 4. So this will be my angle that I can use rather than the negative 19 over pi. In fact, we can put these as equal. They would have equal outcomes. This is equal to the cotangent of negative 3 pi over 4. We know that cotangent is positive in the first and the third, just like tangent. And so for this function going in the opposite direction, 3 pi over 4, putting us into the fourth quadrant, we're going to get positive 1. Now, had we gone positive 3 pi over 4, that would have put me here in the fourth quadrant. And in this particular case, cotangent would be negative. So my answer would be negative 1, where here it's positive 1. So we're getting the opposite of what we would have got. We take the negative of negative 1, which is positive 1, the opposite. And that's why cotangent we consider an odd function. We get the opposite of what we would get had we done it in the other direction. This brings us to the end of this particular lecture. Keep practicing with these things. The more you practice, the more you remember. And the easier these topics, which seem so foreign to us, can really become. As I say, practice makes better.